Welcome back to the deep dive. Today we're ripping the covers off something really fundamental for Java devs, especially if you're aiming for those senior roles. We're talking Java class loaders.
That's right. And it's more than just knowing syntax. Understanding class loading, that's like understanding how your Java code actually wakes up and runs inside the JVM. Super important for tricky debugging and, well, solid system design.
Exactly. It pops up in interviews all the time because, it shows if you really get the runtime. So, our mission today: break down how it works, spot the common traps, and help you talk about it confidently. Turn that knowledge into interview wins.
Okay, let's dive in. It all starts with the basic unit, right? The class file.
The .class file you get after you compile.
Precisely. And that file has the bytecode, the instructions for one class or interface. And these files, they can live anywhere, really.
Like on the file system. Or in a JR.
Yep. File system, JRs, even pulled from a remote server, or generated in memory on the fly sometimes.
Okay, so the file has the instructions. What's the class loader's specific job then?
Its main job is to grab those raw bytes from wherever they are and turn them into an actual class object inside the JVM. That class object is, the live representation of your code.
Got it. The bridge from bytes on disk to a running thing. And Java doesn't load everything up front, right?
No, definitely not. That would be inefficient. It's all on demand. Lazy loading. When your program starts, it loads the main method's class.
Amen.
And then as that code runs and needs other classes, maybe system.out.print needs java.lang system, or you use a scanner, the JVM goes hunting.
A scavenger hunt, I like it.
Yeah. It finds and loads those classes and then their dependencies and so on, only when something is actually needed for the first time.
Makes sense. Just in time. Now, this hunt isn't random. There's a structure, a hierarchy.
Absolutely. Think layers. It's often called parent-child, but it's really more about delegation. When a loader needs a class, it usually asks its parent first.
Hey, Dad, you got this.
Sort of. Only if the parent says, nope, can't find it, does the current loader try to find it itself. This delegation is key for security, stops you accidentally replacing core Java classes.
Okay, trust the parent first. So what are these layers? Who's at the bottom?
The foundation, the bedrock, is the Bootstrap class loader. This one's special. It's usually part of the JVM itself, often native code, not Java.
And it loads.
The absolute core stuff, java.lang, .object, string, the basic runtime classes found in art.jar or the core modules now, the things the JVM needs just to function.
The bare essentials. Okay, what's the next layer up?
That's the platform class loader. It handles other standard libraries, particularly stuff related to Java's module system that isn't quite core enough for Bootstrap. One interesting detail: permissions for classes loaded by platform can sometimes be managed by a security policy, unlike Bootstrap classes.
Interesting distinction. And the top layer, the one we usually deal with.
That's the system class loader, sometimes called the application class loader. It's the workhorse for loading your application classes in third-party libraries, it looks where. On the class path or the module path that you specify when you launch the app.
Right. Bootstrap for deep core, platform for other standard stuff, system for our code and libs. Clear. Now, I feel like there's an interview trap related to checking the class path on these loaders. Something changed.
Oh, yeah. Classic. Gotcha. Back in the day, older JDKs, platform and system loaders, were often instances of URLClassLoader. So people got used to calling get URLs on them to see the class path.
And that's bad now.
It's unreliable. You absolutely cannot assume they are URLClassLoader instances anymore. Trying to cast and call get URLs might just fail or give you nothing useful. It's an anti-pattern, a red flag in an interview.
So if the interviewer asks how to see the system class loader's class path, what's the right answer?
The clean, correct way is to query the system properties. You call system.getProperty with the key, java.class.path, string java.class.path. That gives you the actual class path string the JVM is using.
Okay, system.getProperty, java.class.path. Got it. Don't touch the loader itself for that. Great tip. So, standard hierarchy is clear. But what if my classes aren't on that initial class path, like plugins? Users drop a JAR in a folder later.
Exactly. That's prime territory for custom class loading. The system loader only knows the launch class path. If you need code from somewhere else, loaded dynamically, you got to take control. That's a very common senior interview topic.
How do you take control? What's the usual way?
Well, the most straightforward way for loading from specific JRs or directories dynamically is often to create your own instance of URLClassLoader.
Okay, URLClassLoader.
Yeah. You create it, and you give it an array of URLs pointing to where your dynamic classes live. Could be paths to JRs, paths to directories.
You pointed at the new code location. Yeah. Then how do you load a class using it?
You typically use your shiny new URLClassLoader instance with class.forename, the version that takes 3 arguments. The class name as a string, a Boolean flag, and your custom loader instance.
Class.forename, name flag, loader. Okay, what's that Boolean flag about? That sounds important.
Oh, it's critical. Another frequent interview question. That Boolean flag, the second argument, controls whether the class is initialized right after it's loaded.
Initialized, you mean running static blocks?
Exactly. Static blocks, static field initializers. If you pass true, the JVM loads the class and runs all that static setup code. If you pass false, it just loads the definition but doesn't run the initializers yet.
So true runs the static stuff, false doesn't. When would I want true?
Almost always, if you intend to use the class right away. Many classes depend on static initializers to set up internal state, connect to resources, whatever. If you load it without initializing, with false or using a different method, and then try to use it, things might break because its setup didn't run.
Okay, so class.forename with true initializes. What about the other way, classLoader.load class? I see that method too.
Good catch. ClassLoader.load class string name typically does not run the static initializers. It just finds the bytes, defines the class object in the JVM, and stops. It performs loading, but not initialization.
Right. So if my class needs static setup, using load class directly is probably wrong. It's an anti-pattern if initialization is needed.
Precisely. You'd likely get weird errors later. The safe bet for dynamically loading and using a class is generally class.forename with the true flag for initialization. And note, the simpler class.forename class name, the one argument version, does initialize by default using the caller's loader.
Got it. Class.forename initializes. Class.forename name true loader initializes. ClassLoader.load class name doesn't. That Boolean is definitely key.
Absolutely. Now, URLClassLoader is great for files and JRs, but what if your class bytes are coming from, I don't know, a database blob, or you decrypted them, or maybe you compiled code in memory and want to load it?
Okay, yeah, URLClassLoader won't cut it there. Sounds like you need a totally custom loader.
You got it. You'd extend the abstract ClassLoader class yourself, and the main method you must implement is findClass. Takes the class name as a string.
And what does my findClass implementation have to do?
Its one job is to find and load the raw byte array for that class name. This is where your magic happens. Fetch from DB, decrypt, generate, whatever. Get the bytes.
Okay, findClass gets the bytes, but the JVM needs a class object. How does that step work?
After your findClass successfully gets the byte array, you call a protected method from the ClassLoader base class.
Define class.
Define class.
Yep. You pass it the class name, the byte array, and usually the start offset, 0 in length of the array. The find class does the heavy lifting, verifies the bytecode, turns it into a proper class object within the JVM, and links it up. So typically the last thing your find class method does is call define class with the bytes it found. Okay, so find class finds the bytes, define class makes it official in the JVM. Powerful stuff.
Yeah.
But loading code with different loaders sounds like it could get complicated fast.
You're spot on, and that brings us to a really common and often painful problem. Class loader inversion. It's a classic headache.
Class loader inversion. Okay, what does that look like? I think I've hit this without knowing the name.
Very possible. Imagine this. You have a utility class, util, in your main application, loaded by the system class loader. It has a handy method like create instance string class name, which dynamically loads a class using, say, the simple class.forename class name.
Pretty standard utility method.
Right. Now you have a plugin system. You load plugins from JRs using a custom URLClassLoader. Let's call it plugin loader. The system later knows nothing about these plugin JRs.
Okay.
Code inside your plugin calls util.createInstance upon my plugin some plugin class. The plugin expects util to load a class that's sitting right there in the plugin's own JIR, loaded by plugin loader.
But util was loaded by the system loader.
Oh, exactly. When util.createInstance calls class.forename, class name, which class loader does it use by default?
The loader of the class calling for name, which is util's loader, the system loader.
Bingo. The system loader looks on its class path, doesn't see com.myPlugin, some plugin class, and throws class not found exception. That's the inversion. The plugin expected its context, plugin loader, to be used for loading, but the utility defaulted to its context, system loader.
Oh, okay. I see it now. The context got flipped. How do you fix that?
Couple of main ways. Option 1, change the utility method. Make it util.createInstance. string class name, class loader loader. The plugin code then explicitly passes its own loader, plugin loader, when it calls the method.
Makes sense. Pass the loader explicitly. But what if you can't change util, or it's used everywhere?
That's where the context class loader saves the day. Every thread in Java has one. By default, new threads inherit it from their parent thread, usually ending up as the system loader for the main application thread. But importantly, you can change it.
You can set the thread's context loader.
Yep. Thread.currentThread.setContextClassLoader, your plugin loader. You can temporarily tell the current thread, hey, for dynamic loading purposes, use this loader.
Okay. So how does the util class use that?
The util method, instead of just calling the simple class.forName, class name, can retrieve the current thread's context class loader. It calls thread.currentThread.getContextClassLoader. Then it uses that loader in the 3-argument class.forName, class name true, context class loader.
Ah, clever. Util doesn't need to know about the specific plugin loader, just how to ask the thread for the currently relevant one. What's the best practice for plugins then?
The standard pattern, especially when calling into code loaded by a different loader, like your plugin, is this. 1. Get and save the current thread's context class loader. 2. Set the thread's context class loader to the plugins loader. 3. Make the call into the plugin code. 4. Crucially, in a finally block, restore the original context class loader you saved in step 1.
Always restore it.
Always. Otherwise, you mess up the thread state for later code. Forgetting to restore is a common bug, and an interview red flag is suggesting a general utility should hardcode any specific loader. It should either take one as a parameter or use the context loader. Give the caller control.
That tried finally pattern with set context class loader seems really robust for plugins.
Okay, we've done manual loading, custom loading. Is there a standard Java way just to discover implementations of an interface, like finding all available crypto providers?
Yes, there is, and it's another thing interviewers like to ask about. The service loading framework, using java.util.serviceLoader. It's built specifically for the service provider interface, or SPI, pattern. Think of it as Java's standard way to look up service implementations.
SPI and service loader, how's it work?
First, you define your service, usually a public interface, maybe an abstract class. Let's stick with crypto. Define an interface, com.mycompany.crypto.cipher. It has methods like encrypt, decrypt.
The service contract. Exactly. Then, anyone who wants to provide an implementation creates a concrete class, say com.mycompany.crypto.impia. Caesar cipher, that implement cipher. One key rule. These implementation classes must have a public no-argument constructor because service loader needs to be able to instantiate them easily.
Okay, interface, implementing class with no arg constructor. How does my app find this Caesar cipher? Does it scan everything?
It doesn't scan blindly. The magic is in a configuration file. Providers package a specific file inside their jar, meta-inf services, followed by the fully qualified name of the service interface.
So for our example, the file is meta-inlsservices.com.mycompany.crypto.cipher.
Precisely. And inside that UTF-8 text file, you list the fully qualified names of the concrete implementation classes, one per line. So that file would contain the line com.mycompany.crypto.mpl.caesar If another JR provided an AES cipher, it would have its own meta-infservices.com.mycompany.crypto.cipher file listing, com.mycompany.crypto.mpl.nes cipher.
So the JRs advertise their implementations in that specific file location.
Okay.
How do I use this lookup in my code?
It's pretty simple. You get a service loader instance by calling serviceloader.load and passing the service interfaces .class object. So service loader cipher loader, service loader.load cipher.class. This loader now knows how to find all those configuration files on the current class path or module path.
Okay, got the loader. How do I get the actual cipher objects?
The service loader itself is iterable. The easiest way is often just an enhanced for loop. When you iterate, the service loader finds the classes listed in the config files, loads them using the appropriate loader, usually the one that loaded the interface, and instantiates them using that no-arg constructor.
Simple loop gives me instances. What if I want to be more selective? Find one without creating all of them.
That's where the stream method comes in handy. Instead of iterating directly, you call loader.stream. This gives you a stream service loader.provider cipher.
A stream of provider objects.
Right. And a provider object represents a discovered implementation, but doesn't necessarily instantiate it immediately. It has methods like type to get the class object of the provider and get to actually instantiate it.
Ah, so I could stream, filter based on provider.type, and then call provider.get only on the ones I want.
Exactly. That's a neat optimization if you only need a specific type.
Very flexible.
Yeah.
And methods like find first on the stream would return an optional cipher, right? For when nothing matches.
Precisely. It handles the not found case cleanly. Service loader is really Java's standard, elegant way to build pluggable systems.
Fantastic. Okay, great overview of the tech. Let's switch hats. Imagine you're the interviewer now, and I'm the candidate. Hit me with a scenario.
All right, scenario one. You're debugging a large, complex application. Logs show a class not found exception. Walk me through your diagnostic process, keeping the class loader hierarchy in mind.
Okay, class not found exception. First thing, I double-check the class name in the error message. Simple typo. Happens all the time.
Good start. Then?
Then verify the environment. Is the expected JAR class directory actually there on the machine? Are the file permissions okay? Then check the application's launch configuration. How is the class path or module path set? I'd specifically check the java.class.path system property to see what the JVM thinks the class path is.
Makes sense. What about the loaders?
Right, I think. Which loader should be loading this class? Is it a core Java class, Bootstrap platform? If so, something is deeply wrong with the JRE JDK maybe. Is it an application class or a library? If so, is the JAR actually on the class path I just checked? Or is this class part of something loaded dynamically, like a plugin?
And if it is dynamic loading?
Then I'd look at the code doing that loading. Is it using a custom URL class loader? Is that loader pointed at the right directory, or JAR? And crucially, I'd suspect class loader inversion. Is the code requesting the class loaded by one loader, but the class itself lives in a context loaded by another? If so, is the context class loader being set correctly before the dynamic load attempt? It's about figuring out which loader is trying and what path it's looking at.
Very thorough. You covered environment, configuration, the hierarchy, and the common inversion pitfall. Good. Next scenario. You need to add a feature allowing users to drop custom calculation logic JARs into a folder which your application loads at runtime. How would you design this, and what class loader issues would you anticipate?
Okay, dynamic loading of user code. Sounds like a plug-in pattern. First, I'd define a clear Java interface, say calculation rule, that the user's code must implement. That's the contract. For loading, I could use a custom URL class loader pointed at the user's plugin directory. When needed, instantiate the loader, then use class.forName with the rules class name, true for initialization, and that custom loader. Alternatively, and probably better, I'd leverage the service loader framework. I'd define the calculation rule interface and tell users to package their implementation in a JAR with the meta nff services.com.myapp.calculation rule file listing their class. My app then just uses serviceloader.load calculationrule.class to find and instantiate them. Cleaner discovery.
Both valid options. What potential problems specific to class loaders would you highlight?
The biggest one is definitely class loader inversion again. If the user's calculation rule implementation tries to load its own resources or helper classes bundled within its JAR, but it does so by calling, say, a core utility method in my application, that utility might use the wrong loader system or the default context loader and fail with class not found exception. So the key mitigation is, when my core code calls into the loaded user code, the calculation rule implementation, I must wrap that call, save the current thread's context class loader, set the context loader to the plugins loader, make the call, and then restore the original context loader in a finally block. That ensures the plugin code uses its own loader for its internal needs. Also need to consider resource loading from within the plugin JAR, and maybe security if the code is untrusted.
Excellent. You identified the main risk and described the standard context class loader pattern to solve it. Very good. Okay, one quick direct question. Explain the significance of the true parameter in class.forName. String name, Boolean initialize, class loader, loader.
Right, the initialize flag. Setting it to true tells the JVM to not only load the class using the specified loader, but also to run its static initializers, immediately static blocks, static field assignments. Setting it to false loads the class definition, but skips that initialization step. It's significant because if a class relies on static initialization for setup, and you load it with false or using classLoader.loadClass, which also doesn't initialize, the class might be in an unusable state, leading to errors later. So true is usually what you want for dynamic loading if you plan to use the class right after loading.
Perfect. Clear, concise, and you explain the why. That demonstrates real understanding.
Phew. Okay, so wrapping up our deep dive, we've journeyed from class file bytes through the on-demand scavenger hunt, mapped out the Bootstrap, platform, and system loader hierarchy.
And stressed using system.getProperty, java.class.path, not get URLs.
Definitely. We looked at custom loading with URLClassLoader and extending classLoader using findClass and defineClass.
And hammered home that crucial difference. Class.forName with true initializes, classLoader.loadClass doesn't.
Tackled the class loader inversion beast, and saw how the context class loader, used carefully with set and restore, is the standard solution.
And finished with the service letter framework, the elegant, standard way for SPI and pluggable discovery using Meta in F services.
Getting these concepts down, really understanding them, isn't just about passing interviews, though it certainly helps there. It makes you a much stronger Java developer, able to diagnose those really weird runtime problems.
It shows you understand how the JVM actually works at a deeper level.
So here's a final thought for you. How do these class loading principles apply in modern architectures? Think microservices. Think Java modules, JPMS. They rely heavily on isolation and dynamic loading. How does knowing this stuff help you design better, more flexible systems? Something to cheer on.
Definitely a good connection to make.
We really encourage you to play with this stuff. Look at the Java doc for class loader, URLClassLoader, service loader. Maybe write a tiny plugin system or a service provider example.
Nothing beats hands-on coding for making it stick.
And hey, if this deep dive helped you out, give us a like, subscribe for more tech explorations, and definitely drop a comment below. What are your nightmare class loader interview questions or debugging stories? We want to hear them.
Yeah, share those war stories.
Until next time, keep diving deep.